Welcome to the Explainer. Today, we're going to demystify one of the most crucial and versatile data structures you'll ever encounter, especially if you're prepping for interviews at top product-based tech companies, the graph. It's an absolute fundamental topic in data structures and algorithms, and by the end of this session, you're going to have a rock-solid understanding of exactly what it is and how to build it completely from scratch.
Now look, you've probably heard the rumors from peers that graphs are incredibly difficult. And it's true that beginners often find graph questions kind of lengthy and intimidating. There are just so many moving parts, right? Edges, vertices, weights, algorithms. It sounds like a lot. But I assure you, once we break it down systematically, it's surprisingly simple. It really just takes a little bit of patience to build a clear mental model.
So here is our roadmap for this explainer. Introduction to graphs, real-life uses, types of graphs, how to build a graph, and finally, our C++ code implementation. Let's get right to it.
Section 1, Introduction to Graphs, where we'll break down the core components.
All right, to really get the fundamental architecture of a graph, let's contrast it with something you're probably already familiar with, binary trees. You know the deal there. It relies on a strict parent-child hierarchy. You always know exactly who the parent is and who the children are. But graphs? Totally different beast. A graph is simply a free-flowing network of connected nodes, with absolutely no hierarchy at all. Literally any node can theoretically connect to any other node. It's just pure, unrestricted connectivity.
Now, in graph terminology, we give these nodes a specific name. Each individual data point, or entity in this network, is formally called a vertex, or vertices if we're talking plural. You can just think of a vertex as an individual location or pin on a map.
And what about the physical links connecting one vertex to another? Well, those are our edges. Kind of like the branches in a tree data structure, an edge just represents a direct relationship, or path, between two vertices. Moving on to Section 2, real-life uses, and exactly why this data structure matters so much.
Because look, graphs are definitely not just some abstract academic concept. They are quite literally the backbone of modern technology. Think about Google Maps or Uber. When you need to travel from city A to city C, those cities, they're vertices. The roads, edges. The app is basically calculating the best path through that massive graph. Or look at Facebook and Instagram. Your profile is a vertex, and your mutual friendships are the edges connecting you to a global social graph. Even under the hood of machine learning, those incredibly complex neural networks powering AI, yeah, they're structured entirely using graphs.
Section 3, Types of Graphs. Let's classify them by edges and weights.
So, depending on the exact real-world problem you're trying to solve, the behavior of these edges is going to change. First, let's look at direction. A graph can have unidirectional edges, which basically act like a one-way street. You can travel from vertex 1 to vertex 2, but there's no way back. On the flip side, we have undirected graphs. These act more like a mutual, bidirectional friendship on Facebook. If person A is friends with person B, while person B is naturally friends with person A, traffic flows freely in both directions.
And edges can also hold specific values, which we call weights. Now, we aren't talking physical weight here. It's a metric. For instance, an edge might have a positive weight representing a 10-kilometer distance between two cities. Or, wild as it sounds, it could even hold a negative weight, like negative 10 rupees, representing a cost incurred to travel down that specific path.
So when we combine those two traits, direction and weight, we generally run into 4 main variations during coding interviews. We've got the undirected and unweighted graph, which is definitely the simplest form. Then we have undirected and weighted, directed and weighted, and finally directed and unweighted. Honestly, whenever you read a graph problem, figuring out which of these 4 you're dealing with, that is always step 1.
Now, here's a really crucial point. We usually just assume all nodes in a graph are linked together in one big cluster, right? Well, actually, scratch that. It's not always true. You can totally have disconnected graphs. This is where components exist completely isolated from one another. Imagine a social network where a group of 3 friends are super connected to each other, but they have 0 mutual friends with literally anyone else on the entire platform. They're part of the same overall graph, sure, but they remain this disconnected, isolated component.
All right, Section 4, How to Build a Graph, bridging the gap from our visual model to actual code.
Okay, drawing circles and lines on paper is awesome for our human brains, but computers need highly structured data. To represent this visual network inside a computer, the absolute most popular and efficient method is using what's called an adjacency list. The concept is wonderfully straightforward. We just go through every single vertex in our graph and record a literal list of its direct neighbors.
Let's map it out. If we examine vertex 1,
We look at the edges and see, okay, it directly connects to vertex 0, vertex 2, and vertex 3. Boom, we just mapped this out for the whole network. Vertex 0 only connects to 1. Vertex 2 connects to 1 and 3. By doing this systematically, we capture the complete geometry of the graph right inside a simple table.
But how do we actually store this table in memory? Well, because the total number of vertices can vary wildly, like one graph might have 4 nodes and another might have 5,000, we really try to avoid static, fixed-size arrays. Instead, we use a dynamic array of lists. This is a total game changer because it allows our data structure to dynamically stretch and perfectly fit whatever graph size we throw at it during runtime.
And finally, Section 5, C++ code implementation, where we write the logic.
Now that we've got this perfect mental model locked in, let's translate our adjacency list into C++ using the standard template library. This is where all that theory becomes real, tangible logic. We're going to execute our code in 3 super digestible steps. First, we'll set up our main graph class and initialize our dynamic structure. Second, we'll write the add_edge function to actually populate the graph with data. And third, we'll just write a quick loop to print the results to the terminal and verify our work.
Let's zoom in on step 2, populating the graph. Honestly, the entire logic of the add_edge function boils down to this one simple rule. If we have an undirected edge connecting vertex u and vertex v, we just append v to u's list of neighbors. And then we do the exact reverse. We append u to v's list. It's just a simple two-way handshake in the code. Of course, if the graph was directed, we would just do the first step and call it a day.
So, under the hood in C++, we're using a pointer to an array of lists. This essentially creates an array of size v, representing our vertices, where each individual index securely holds its very own doubly linked list of integer neighbors, provided right out of the box by the C++ standard template library. So, index 0 holds its list, index 1 holds its list, and so on. It's incredibly clean.
And this brilliantly illustrates our final outcome. When we wrap up the code, run the build, and use a simple loop to print out the array indices alongside their lists, the terminal output perfectly matches that manual adjacency list diagram we drew earlier. Just like that, our code has successfully captured a complex, unstructured network into highly efficient computer memory.
So, we have successfully built our graph from scratch. But storing the data, that's really only half the battle. Now that the graph actually exists in memory, it leaves us with a fascinating, absolutely critical question for our next explainer. Once this thing is built, how do we systematically travel through it to actually search for data? Well, breadth first search and depth first search hold the answers, and let me tell you, they are incredibly fun to learn. So until next time, keep exploring.